Hello, hello, hello. This is Nicholas on this lovely Wednesday afternoon, and I just found out that mayonnaise is the type of enzyme that aids in the digestion of a BLT. Now, I wanted to talk today about something kind of cool. I've been doing some number theory lately, about generating what's known as a primitive. So, say what that means. Primitive Pythagorean triples. So we all are familiar with the Pythagorean theorem. It says that, whoa, that was a really bad line. There we go. It says that if you've got x squared plus y squared, namely sides of a right triangle, legs specifically of a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So it's triples of numbers. So a more formal definition for Pythagorean triple specifically is that so it's a triple of numbers. A triple of numbers. Say we call them x, y, and z, like how I did there. It's x, y, and z that are an element of natural numbers, and I write n cubed because it's a triple of ordered numbers. Another way you can think about it is that each one of them is a natural number. So n, n, and n. If x squared plus y squared plus z squared equals 1. And also, if the GCD, the greatest common divisor of x, y, and z, is equal to 1. So what this means, for example, is that probably the most famous Pythagorean triple is the triple 3, 4, 5, right? Because 3 squared plus 4 squared is equal to 5 squared. And the GCD of those set of numbers 3, 4, and 5 is indeed 1. Now, for example, the Pythagorean triple 6, 8, 10, while it is true that 6 squared plus 8 squared is equal to 10 squared, this really isn't all that interesting because it's just a scalar multiple of this original, what we call primitive Pythagorean triple, namely 3, 4, 5. We just multiplied by 2. So we're interested more so in primitive Pythagorean triples here, so where the greatest common divisor is 1. Now, just some notation here that I'm going to talk about before I dive into generating Pythagorean triples is what's when I talk about the dividing function, or in other words, how I notate divisibility. So let's say we've got a and b, so divisibility. If we've got a and b integers, and a is not equal to 0, then we say that a divides b, right? And we write it as a with a vertical bar. A divides b is how that's read. And another way of saying that is that b is equal to ka. So a is a multiple of b if b is a multiple of a if a divides b. So, for example, 2 divides 16 because 16 is equal to 2 times 8. Or, for example, 3 does not divide. We'll do a little dash through it. 3 does not divide 91 because 91 is not equal to 3k, element of the integers. Namely, k would have to be 91 thirds, which is not an integer. So that's the notion of divisibility. Now, 3 important properties, well, really 4, is that we have essentially transitivity with divisibility. So if a divides b and b divides c, then a divides c. We have the notion of distributivity. So if A divides B, then CA divides CB. So for a scalar C, integers, of course, we're talking about. And then we have the third more interesting property that essentially combines these two. So if A divides B and A divides C, then A divides any linear combination of B and C. So A would divide BX plus CY. Again, X and Y being integers. So you can go through and kind of prove these for yourself if you want. This last one is especially important, and we're going to use it. And one other thing that should be fairly obvious to note that is if A divides 1, then A necessarily has to be equal to plus or minus 1, right? Because if you have 1 is equal to K A, and K has to be an integer, well, then A has to be equal to 1 or negative 1. Otherwise, K would not be an integer. So now I have divisibility set. Now we can dive into primitive Pythagorean triples. So the first question that I would want to ask to you all is, so we talked about 3, 4, 5. Maybe another one is 5, 12, 13. Those are two of the more known Pythagorean triples. So the question I want to ask is here, it looks, this is basically to consider the parity, whether the numbers are even and odd. So is it possible that X and Y can both be, say, even? And I ask this because here one's odd and one's even, here one's odd and one's even. So can X and Y both be even? Well, if X and Y are both even, then that means that, for example, that we could say X is equal to 2A for another integer A, and Y is equal to 2B for another integer B. And then that would imply that X squared plus Y squared is equal to 4 times A squared plus B squared, which is equal to Z squared. So that would imply that 4 divides Z squared, or in other words, 2 divides Z. And so that would imply that Z is also even. But if X and Y are both even and Z is also even, then the GCD of X, Y, and Z is going to be at the very minimum 2. And so that's not equal to 1. And so that if they're both even, then you have a Pythagorean triple that's not primitive, not what we're looking for. So in the case of primitive Pythagorean triples, no, X and Y cannot both be even. Now the accompanying question then is, X and Y, can they both be odd? Naturally. So let's see, you're probably thinking no, and you would be right. So if they're both odd, then X is equal to, say, another 2A plus 1, where A is another integer, and Y is equal to 2B plus 1 for another integer B. And so X squared plus Y squared is 2A plus 1 squared plus 2B plus 1 squared. And when you FOIL that all out, you're going to get 4 times A squared plus B squared plus A plus B plus 2 is equal to Z squared. Now, Z squared is a perfect square, right? And so this on the right side here, or I'm sorry, on the left side right here, has a common factor of 2 in both of these terms. So Z squared would be a multiple of 2. So in other words, we have a perfect square that's multiple of 2. But Z squared is not a multiple of 4 because of this plus 2 right here. So there, and the point that I'm trying to make is that if we're considering natural numbers, right, Pythagorean triples, natural numbers, then Z squared cannot be in n, because there is no perfect square that is a multiple of 2 but not a multiple of 4. And that should make sense because the smallest perfect square is, well, 1, right? Obviously there's 0, then there's 1, and then there's 4, and then there's 9, and then so on and so forth. So 1, obviously you have no factors of 2 anywhere in there, but the next biggest square requires, obviously if it's a square, requires 2 factors of 2, and so it has to be a multiple of 4. And so any other perfect square that has a factor of 2 in it has to have another factor of 2 in it, and therefore has to be divisible by 4. So a perfect square, if it's divisible by 2, it's got to be divisible by 4 as well, because it has to have 2 factors of 2 in there. Otherwise, it's not a perfect square. So no, x and y cannot both be odd. So that means that one is odd and one is even. So without loss of generality, let's say that x is an odd and y is an even number. So then what we can say is that, if x squared plus y squared is equal to z squared, now we have an even squared. So an even times an even is still an even, right? And an odd times an odd is still an odd. So we have an even plus an odd, which gives us an odd. And so this the square of an odd then will still be, or the square root of an odd will still be an odd. And so that means basically what I'm getting to is that z also has to be odd. So, and you can go through the algebra there too. If you want to if you want to do 2a plus 1 squared plus 2b squared and set that equal to z squared, and do it that way too, you can. I just kind of skipped a couple steps there because I think it's not all that difficult to show. So now, let's say now then that, oh, hey, Miles. So that's says that y squared is equal to z squared minus x squared. So I'm going to isolate the one even on one side and put the odds on the other side. This side right here is just begging for difference of squares. So that's z minus x times z plus x. And now, again, let's look at the parity of both of these factors. See, z is odd, x is odd. So their difference will have to be even. And likewise, this is odd and this is odd, so their sum will have to be even. So what that means is that z minus x and z plus x are both even. And so what we can then say also is, noting the fact that y is even as well, we can write, for example, that 2k squared is equal to, say, 2m times 2n. Because if they're both even, you can write them in the form 2 times another integer. And so we're going to get that 4k squared is equal to 4mn, or in other words, that k squared is equal to mn. And now from here, my claim now is that for this to be true, so my claim here is that for this to be true, the GCD of m and n has to be equal to 1. In other words, m and n, those look awfully similar. M and n are relatively prime, as it's also sometimes called. That just means that they share no common factors other than 1. So how can I go about that? Well, let's say that there is some other nebulous divisor. Let's suppose the contrary. Let's say that there is some greatest common, there's a number greater than 1 that divides both m and n. So we're going to suppose that there's a divisor d that divides m and D divides N. So then if it divides M and it divides N by this property right up here, it's going to divide any linear combination of M and N. So that means, that D will also divide M plus N. Now, M plus N, of course, is the same thing as D divides Z, because one thing to notice is that, how did we do it right here? We said, okay, we let Z minus X right here. This was 2M, and then this here was 2N. So if I were to write out explicit formulas here for M and N, maybe I'll do it in yellow. We have, whoa, that's way too faint. Yellow is not a good idea. So we have Z minus X is equal to 2M. And so that means that M is equal to Z minus X over 2. And N is equal to Z plus X over 2. So what I'm getting at here now is M plus N then is Z minus X over 2 plus Z plus X over 2, which is nothing but Z. So D would also have to divide Z. Now, if D divides Z, well now, also right here, if D divides M and D divides N, then it divides any linear combination, so D also has to divide M minus N, which means that D divides X, because M minus N is nothing but Z minus X over 2 minus Z plus X over 2, which is nothing but X. So now what that tells us is that D divides Z and D divides X. So if D divides Z and D divides X, then D divides the greatest common divisor of X and Z. Now, the greatest common divisor of, okay, well, first of all, if this is true, if D divides Z and D divides X, right, then it's going to divide any common factor that they have between them. And so if we're concerned about the greatest common factor or the greatest common divisor, then let's use that quantity right here. Let's use the GCD of X and Z. So now I will show, and kind of like a sub-lemma here, that the GCD of X and Z is indeed 1. So that would mean that D would have to divide 1. If we're thinking with natural numbers here, that implies then that D has to be equal to 1. And so the greatest common divisor then of M and N is 1. Now, my kind of little lemma right here about the GCD of X and Z being equal to 1, I'll also do via contradiction. So let's say it's not 1. So let's suppose instead that the GCD of X and Z is, say, equal to another integer, call it L. Just random letter there. So then, if the GCD of X and Z is L, we know that y squared is equal to Z squared minus X squared. But if they both share a common factor of L, then that's the same thing as writing for another Z, call it Z prime L squared minus X prime L squared. In other words, basically Z prime is Z divided by L, and X prime is X divided by L. So I'm just replacing them with another Z and multiplying by their common factor, their greatest common factor L, which would imply then that L squared divides Y squared, which would imply that L divides Y. But if L divides Y, and it divides X, and it divides Z, then the GCD of x, y, and z is equal to L, which is not equal to 1. And so we don't have a primitive Pythagorean triple. So therefore the GCD of x and z does need to be equal to 1 for a primitive Pythagorean triple. Then another thing that is necessary to see that is that if we've got x, y, and z as a primitive Pythagorean triple, and we have that k squared is equal to mn, is basically what we reduced down to, this type of Diophantine equation. So if this is true, if k squared is equal to mn for integers, and the greatest common divisor, so with the greatest common divisor of m and n being equal to 1, like I just proved, what is it, in this part right here, then it also necessarily follows that we must have that m itself is another perfect square, say p squared, and n itself is also its own perfect square, say q squared. And those two numbers, the GCD of p and q is also 1. In other words, p and q themselves are also relatively prime. So what we get then is that k squared is equal to p squared q squared. And why this is true, I would probably leave as an exercise for the viewer, though it should be pretty obvious to kind of guess why this is the case. If m and n are relatively prime, and you have a perfect square meaning it needs two factors of the same, it needs two of the same factors, but you're not allowed to, multiply m by itself, because then you wouldn't keep this condition upheld. Then the only way that's going to happen is that if these numbers are themselves perfect squares, in other words, they intrinsically already have two factors, but those two factors are different from each other. That's basically the quote proof right there. So now we said before that up here in green that m is z minus x over 2 and n is z plus x over 2. So that means if m is equal to p squared, then p squared is equal to z minus x over 2, and q squared is equal to z plus x over 2. Okay, so then 2p squared is equal to z minus x, and 2q squared is equal to z plus x. And so that means that originally, y squared, in the original Pythagorean theorem, x squared plus y squared equals z squared. Y squared was equal to z squared minus x squared, which is equal to z minus x times z plus x, which was equal to 4mn, which was equal to 4p squared q squared, which would imply then that y is equal to 2pq. And so that would also imply that x, oh my gosh, if you take these two equations and add them together, that x is going to be equal to q squared okay, let me do the addition. 2p squared plus 2q squared is equal to z minus x plus z plus x. Oh, so I sorry. So then this is z. So 2p squared plus 2q squared is 2z. So then z is equal to q squared minus p squared, and x is equal to, oh my gosh, z is equal to q squared plus p squared. I added them together, and then I'm taking out the factor of 2. So then x is equal to q squared minus p squared. Again, with the GCD of p and q being equal to 1. And actually, at this particular point, we're we're done. Let me draw that a little better, but now we have a way to generate all possible Pythagorean triples, and it's with this exact method in red right here. So for example, it's just generated by using these formulas right here for x, y, and z, and just picking two integers, natural numbers, that are relatively prime with one another. In other words, their greatest common factor, greatest common divisor, is 1. So for example, if I let p be equal to 1 and q be equal to 2, because those are relatively prime, x, let's say x, y, z, then would be equal to, well, x is q squared, which is 4 minus 1, which is 3. Y is 2 times p, which is 1, times q, which is 2, so that's 4. And z is q squared plus p squared, so it's 4 plus 1, or 5. And so that's how that original Pythagorean triple right there is generated. And so in this way, we can generate every possible Pythagorean triple just based on elementary addition, subtraction, and multiplication of any two relatively prime natural numbers. So with that being said, I think